This is a lecture about visualization. It can be an entire course on visualization. I've taught such courses. It's really a very rich area, and there's a lot to be done with it. But it's absolutely critical for data analysis to understand a little about the principles behind visualization. There's an entire science of perception and sort of physically how your body perceives visual cues. And it's definitely pertinent to how you produce visualizations of data, not just for other people, but for yourself, because you have to rely on your own visual perception of the data in order to understand what you're looking at and know what kind of questions to ask about the data. So this is an overview of a lot of different topics related to visualization. So the first thing I want you to do, I'm going to give you about 30 seconds to look at this next slide and count the times the number of 7 appears. Okay, so sevens that you thought you saw, so you should make a note of that, and we'll see how many there are here in a minute. But the first thing I want to do is ask you to think about whether this makes it easy. Highlight them, might as well make them a little bolder because that makes it even easier to see. Underlying them another accent, so you're making it even easier to count them now. So we've just seen that you could use color, you could use the size, we could have tilted the sevens, orientation, or textured it. Any of these things are what we would call pre-attentive attributes. They don't require any thought or effort to distinguish the sevens. All of these things automatically trigger your mind to recognize them as different. It's a very valuable thing because you're saving mental energy to highlight something important from a number of different ways here. Now, if I had put them all in the same place, that would make it even easier to count them because now they're separated. I can make the background vaguer. That makes it, dulling out the background highlights the sevens, which is what you're interested in. I could create a histogram here of bar charts showing the number of sevens, and in fact you can see now there were 17 of them. So if you counted 17, that was right. Usually when I do this with live classes, a few people, maybe even half the class, will get 17s. Occasionally you'll see a 16 or 18, and then pretty rarely you see some numbers that are different than that. Much more valuable than this bar chart is to actually order it. Anytime you do a bar chart, I would suggest ordering it either in ascending or descending order. Makes it not just easier to see, but also you get additional information. So by ordering it, you can see that 7 was one of the least common numbers there. There were actually twice as many 3s as 7s. If I had asked how many more 3s are there than 7s, that would have been a much more difficult task from the original data. Now it's trivial to answer given this bar chart. We could use a pie chart, and this will be one of the last pie charts you see in this course, except for the others that are in this presentation. Pie chart is not a good way to display anything. I would go so far as to say anything. Certainly in this case, it is not a useful way to display it. The problem is the labeling. The colors are meaningless and just sort of, they're colorful, but they don't convey any information. Makes it very hard to compare. Slices of a pie are difficult. Blue is greater than this color out here where the 17 is as the sevens. So you can tell the blues are greater than the one that's indicated by 17. But can you tell it's twice as big? Much harder to gauge sizes from slices of a pie. In this one, look at the colors and look what happens as the word goes down. It's exactly the same colors in the word data. It didn't change. So when you go down, it looks like it has completely changed color because of the background. There's what was used. It's actually, that's the true color in both cases. Look at a typical kind of bar graph here, and you'll notice the bottom one is a lot easier to read. What's wrong with the top one is we've got too many grid lines, and this is Edward Tufte, who has written some wonderful books about visualization. He calls this chart junk, non-information in the graph. So the lines across are not conveying any information, but the problem when you have them bold is worse in that it obscures the data. So the interesting thing is the lines, the 4 colored lines, 4 different years, and it comes out much more clearly in the bottom one where we have a reduced number of grid lines and they are made much more opaque. An important principle with visualization is the Gestalt principle, and this is the idea of closure. Our mind will automatically close things without any effort. It's automatic that we fill in blanks. And this applies to things that you visualize. It applies to stories as well. If you hear fragments of a story, you will end up filling in the missing pieces. It's automatic, it's instinctual, it doesn't require effort. So in this case, you can look at these and look at this letter here. What letter is it? Could be an H, could be an A. If you surround it, then you complete the letter in the middle depending on what's around it. So it can either be an H or an A, and your mind will automatically do that completion. Stare at the dot in the middle of this picture. I'm going to stare at it for a few seconds here. You notice what happened? This is a black and white photo. But when you stare at the dot here, that color is getting imprinted. And the first look at this picture looks like it's color, but it's actually black and white. Stare at this dot. Now you've seen a ghost. There is nothing on this page, but if you stare at that dot, it imprints that picture long enough that when you go to this, you can still see the picture for a while before it fades away. So some points about visual perception. Most of our sense receptors are in our eyes, and a lot of our brain is occupied with processing visual information. That has more bandwidth than any other receptor or sense that we have. I really don't know enough to speak to this, but I think it would be very interesting to know how this works for people who are blind. Because if they're blind, I suspect that the way the brain processes information is different, and probably depending on whether they've been blind from birth or when they became blind. But I don't know anything about that, but I'm sure there is some research on that that you can find. And visual perception is very much connected to understanding. And if you look at language, in the English language, we have a lot of examples where visual and understanding are connected. I see what you're talking about, sketch out an idea, seeing is believing. An important principle is that our working memory is limited. So we don't have space to put too much information into our working memory. Visualization is a way to take a lot of information and reduce the amount of working memory that is needed to understand it. How do we do that? Let's talk about color first. I actually frown upon the use of color. I will use plenty of color, but I use it sparingly. You want to use it intentionally. Using color to make something colorful, even worse, to take something that is boring and make it colorful. That is a very bad idea. If you have a presentation that's boring, the way to solve it is not to it's to change the content of the presentation. And I use that a lot. The blue kind of looks more attractive than using white to black, but white through gray to black works perfectly fine. And if you're using, but it's okay. Lighter means less. You don't get precise measurements, so whether you box, is it 50% more than the first box or 30% more? You can't tell that from this kind of display, but you can easily tell more and less. That is harder when you use multiple colors. So when you look at like the categorical scheme, where every category is a different color, it distinguishes between them, but the colors don't themselves have any meaning. So it is often not the best way to make displays. All it achieves is distinguishing between the categories. It doesn't say anything about more or less. It hides that information. A diverging scheme can be useful if you want to distinguish the negative, profits and losses. But you have to be careful about whether you're using colors that have any kind of natural interpretation or the colors just, you see the right-hand colors work for me here. The darker means more of the blue. The left hand doesn't work as well because it's not obvious to me that the left-hand box is more than the middle or the box to the right of there. So I would prefer a different diverging color on the left. Highlighting is a very good use of color, where you want to, we saw that with the sevens, highlight something, it draws your attention to it very quickly. It's a pre-attentive attribute that your mind is picking up on. And if you use something like red, it's often an alert. It's not just highlighting, but it's a warning of some kind of danger or something to pay extreme attention to. Here's an example where color does not work. It was in the Wall Street Journal many years ago, but you can find lots of examples in publications today where things are made colorful for no particular good reason. And when you try to understand what the colors are doing here, here's a little closer view of it. It's almost impossible. The colors don't convey any information here. And all they do is divert your attention from the actual graph. So when you draw a graph and you put color in it, the question you should ask yourself, is the color conveying information? If there's no information in the color, don't use it. Or better yet, if you want some information to be conveyed on there, think about whether you can use color to convey actual information about the data, as opposed to just using color in not a thoughtful way. Ordering is another pre-attentive attribute. Our mind automatically can interpret orders. So here's a number of treatments paid for by different insurers, medical insurers. And there are different amounts here, but again, this is an example where if you order it, much more useful information. So, and in JMP, you'll find if you right-click on the horizontal axis, the x-axis, it can actually either axis. If they're categories, it will give you the option to order either ascending or descending order. And it's much better display when you order it. Another thing about the way the mind works is that we have two kinds of systems that work in the brain. The system one is an automatic mechanism. It's actually sort of it's a biological, it's an evolutionary thing that our mind has adapted to use system one automatically, quickly, with no effort. System two is what we often think of as rational thought. We exercise, it takes effort, and our minds, our brains are actually lazy. It's not a pejorative term of calling people lazy. Our brain is a lazy organism. It is evolved to try to minimize effort. So it takes effort to make the brain work for rational thought and system two thinking. And as much as I've been trained through years and years of school to think of my mind as rational, probably 90% or more of, and we wouldn't be able to survive without system one. Our minds have to work automatically, and when we were sort of in the jungle subject to predators, we evolved so that loud noises made us climb trees or pick up rocks or react automatically to stimuli that had important information in it. So system one is absolutely critical for life, but it actually doesn't work very well for data analysis because system one is not evolved. We didn't, as humans, evolve to do data analysis. That sort of requires an effortful use of the brain. So that's system two thinking. And the problem with system two thinking is that system one is never gone. It's still there. And so you have to be aware of it, because even if you think that you're using rational thought, system one may be doing something else that is actually at odds with that. The book Thinking Fast and Slow, written by Daniel Kahneman, who won a Nobel Prize, is an excellent book for talking about how system one and system two interact. So system one can have biases, and that's what we have to be wary of. So if you look at this and you ask what's happening here, this is also an example of the Gestalt phenomenon. Your mind will make up a story to go with this picture, and it's automatic. And it may or may not be true. It may have nothing to do with this. We don't know where this picture came from. But very quickly we create, this is system one at work, we create stories behind what's going on in this picture. Now, what does system one do with something like this? Before you know it, and system two is trying to figure out this graph, system one has already basically processed this information, I would say leading to confusion, basically, who knows what's going on here? Who knows what this is about? Even if you knew the substance of what these surveys were and the response were, all of the visual cues that are coming from this are at odds with that message. They're not productive. So if you oversimplify things, you can get distorted understanding. And if you overcomplicate it, you end up with little or no understanding. It's a very fine line between over and under simplification. So here's a typical pie chart. You'll notice the caution at the bottom here. I like this pie chart. I happen to like pie, and that's a good one. Here's a great presentation about pie charts. Notice how the adjustments are being made to this improve the pie chart. And as it turns it into a bar chart, it actually becomes far better. So I like that presentation. It's an example where you have a pie chart and you can see very easily how it becomes a better display when put as a bar chart. Even worse than a just bad pie chart is a pie chart that doesn't make any sense at all. This was an actual pie chart from Fox News in 2012, and when the percentages don't add up to 100%, it's not clear. That's the only thing the pie chart does, is it tells you that things add up to 100%. And if that's an important piece of information, my suggestion would be put it in the title of the graph and just say shares, or shares of candidates, or candidate shares, and you can put in parentheses total 100%. You can get across that information. You don't need to have the pie to indicate 100%. And in this case, of course, it doesn't even indicate 100%. So general rules for pie charts is, first, make sure that it adds up to 100%. Don't have too many categories. Put things in some kind of order, because we're used to looking at clocks and thinking clockwise. Order them in terms of size. Add the labels. Don't put in third dimension. Keep it simple. And really, the first one's the one I would say don't use them. In lieu of pie charts, you can use a bar chart. It is a far better way to convey information. And here's a stacked pie chart where you can take that and put it all in one bar. But stacked bar charts you have to be really careful with, because, in fact, I would say almost never use them. This one, comparing it to anything, it's just to indicate the 4 categories. But when you want to compare this for, let's say, different years, stacked bar charts are very difficult to interpret, because the bottom, the biggest part at the bottom, you can indicate the size from one year to the next, but all the other slices are much harder to tell which ones are bigger or smaller. So I would use side-by-side bar charts where they're separated, rather than a stacked bar chart. This is a really nice pie chart. I accept this one. And this is a nice, funny pie chart. This is a very bad pie chart. It's an example of all the things you shouldn't do. And a bar chart from this is known as a tree map. And when you've got different relations, the rectangles are proportional to the size of the populations. It's very easy to convey relative sizes with this. And you'll notice you can add the dimension of different regions of the world, different continents, by coloring them differently and putting them into their own sort of section. You also notice they're ordered so that from the top to smaller. So it's actually quite a lot of information can come out of a tree map like this. Showing the number of letters people use in the word goal. This was during the second round matches of the World Cup in 2014, I believe. And so in different matches, you'll see for each of the goals how long was the word goal in their tweets. Sparklines is something that was invented by Edward Tufte. You'll find they're built into Excel. They can be very useful. He sued Microsoft for stealing sparklines from him. I don't know what the outcome of that suit was, whether Tufte won or not, but Tufte clearly invented the sparkline, which Microsoft then adopted and I guess didn't pay him for. It can be used a lot in medicine. That would be a useful way. You can see these are glucose readings, and you can see little time graph. And if you do this in Excel, it'll appear only in one cell of the table. So very shrunken down graphic, but makes it very easy to see what the time trend looks like and maybe compare it across different people or different different days or different years. You can also highlight at the end here to see where the ending reading was. You could shade in the middle to show where, let's say, the middle 80 or 90% of the data is. Then you're getting some additional information in a very small display, actually. Small multiples is an example of a principle that is underused, in my opinion. We tend to think that if you have a picture or something like a map, you want to make it big. But if you want to compare things, think of a PowerPoint presentation. We have a big map, and then you go to the next slide, another big map, another big map on the next slide, and you're trying to compare them from one slide to the next. Short-term memory does not keep these things active. So as soon as the slide disappears, people's brains throw out that information and go on to the new thing. Small multiples gets across a lot of information in a comparative way in a fairly small space. You lose the detail, so you can't really tell which states have droughts in which years, and can't tell the severity of the droughts, but you can tell whether there's more or less drought, so you can certainly see periods of time when there was a lot of drought. So we should, in 1930s, the Dust Bowl year here in 1934, when almost the entire country was in drought. And that's more than any other year, although 2012 was getting pretty close. Making that a little bigger, you can see this, a lot more information. So exactly how the coloring is at the county level here. So there's actually 1,300 counties being represented in this picture. A box and whisker plot we will make a lot of use of. It's a very concise summary of the data distribution. It's concise because you lose a lot of detail, but you still get some important details. You can see where the bottom, the lowest and the highest point is. You can see where the first 25% of the data, what values take you to the 25%. The box in the middle is the middle 50% of the data, with the point in the middle being the median, the halfway point in the data. So half of the data is above that value, this value, and half of the data is below it. Most box and whisker plots, you'll find that the don't actually extend to the end of the data. If there's outliers, enough points that are far enough away from the rest of the data, there will appear as scattered points out here. And this first point won't actually be the lowest value, but the lowest value that is at least in the vicinity of the rest of the values. So most box and whisker plots look like this, with a scattering of points off the ends that are outliers. But you can see where the 25, 50, 75% point of the data is, and one way or another you'll see where the minimum and the maximum values are. So it's a quick way to look at a distribution, and when you want to compare different distributions, it becomes very effective, like in this example. Here we have two different kinds of salary distributions. Market, and you can compare the distributions where the variable it is. So box and whisker plot is a very concise display that gives you quite a bit of information. So that's a whirlwind tour of different types of visual representations of data, things to think about. JMP in particular makes it very easy to change display types. So if you look in graph, a bunch of icons for different kinds of graphs, different kinds of data. Some of them work well and some will work really badly, but it's extremely easy to just change the type of the graph by just clicking on that and letting your own eyes do the work of whether that display is effective or not. It's not just for the people you want to display it to. It's not just for their benefit. It's for your own benefit. When you're trying to figure out what's interesting in this data, what is the story in this data, your eyes are going to do a lot of that work. And so you need a picture that says to you what's interesting. And if it's interesting to you, then hopefully it's going to be interesting to whoever you're presenting it to. So you're doing the work of the presentation as well as the work for your own analysis. And the more you work on the displays, the more you look at every bit of ink that's in the display and ask yourself, is this meaningful? Can I remove it? The more you remove irrelevant ink, the more you have only data that, or ink that is conveying information, the more effective the display will be. And we will get plenty of work examples to try this out on.